All right, so what do you think it was supposed to be? 1 star cosine? Minus, 1 minus. We're trying to evaluate the limit. What does direct substitution give us? Cosine of 0 is what? 1. So we get 0 in the top and 0 in the bottom. Yay! And again, the 0 in the bottom is causing the problem, but there's no factor of x that we could do anything with in the top, so we'll have to graph it and memorize the result. Maybe. We haven't graphed it yet. I put it in Y2. This time I used the horizontal division bar. And zoom 6 will work. And check it out near the origin. Yeah, it looks like it's passing through the origin. Of course, if you hit trace, type in 0, you'll get nothing. But 0.001, you'll see that it's really small. 5e to the negative 4th, right? Really, really small. So from there, you can kind of ascertain that the answer is 0. Yes, and it is. So sine of x over x as we approach 0 is 1, and 1 minus cosine x over x is 0 as we approach 0. So those two you have to memorize. All right, so now that we know that, see if you could do the following. The one right below it is x over 1 minus cosine x. What do you think it is? 0? Very good. This one was only 1 over here because the reciprocal of 1 is 1. This one is the reciprocal expression, so it should be approaching the reciprocal of 0, which is d and e, because it's some type of infinity. And it's the general limit, so it's probably approaching different ones from either side. In fact, it is because we saw the graph of the cosine do this. So if you reciprocate that, it's going to go down on this side and up on that side. So it's a vertical asymptote, it's d and e. So we can't flip that one and get a number, but we do know the result. What did I intend this one to be? You think that's negative x?
Well, I have the paper form, and it's like slanted boxes.
Oh, let's try this one. I'll just make that one up. It's good enough. 1 minus cosine of negative x over x. What's that one? Negative 1? You still get 0 over 0 when you plug in. What type of symmetry does cosine have? Y-axis, right? It's an even function. So what does an even function mean? It means a positive x and a negative x have the same output. So remember, this is the same. For cosine, you can just forget about it. Remember? You could just drop it. So that would be exactly the same, and that would be equal to 0 as well. What about this one? Y0. What is replacing x with x ninth do to the graph? It stretches it horizontally by a factor of 9. So it does change the graph everywhere except when x is 0, because 0 times 9 is 0, so it's still 0. Similarly here, as we approach negative 7, this one's still 0 because the x plus 7 now shifts our graph to the left 7, and that happens to be the value we're approaching now. Well, it was at 0, now it's negative 7, so that one's still 0, so you get the hang of it. Yeah, cool. I know what I wanted to do. Let's add this one in here. The limit as x goes to 0 of cosine of x minus 1 over x, not 0, over x. Now that's different, right? Because 1 minus cosine over x was 0. What is cosine x minus 1? Subtraction in general is not commutative, right? It's the same thing? Why is it the same thing? Cosine of 0 is still 1.
That's the other way, it would make cosine negative, right? If it was 1 minus cosine.
Right, exactly. In this case, it's the cosine that's negative and the 1 that's positive, and here it's the other way around. Well, let's see. This is going to kind of get into what we're going to be doing with these things once we memorize them. If we can manipulate that into something that we've already memorized, then maybe we can use our previous results to get the answer. So let's go ahead and do that. We're used to seeing the 1 first, like we just memorized. So negative 1 plus cosine of x over x. But that's not good because now the signs are off, yeah? So let's just factor out a negative 1. And we get 1 minus cosine of x all over x. And of course, we got properties of limits now that tell us we can split that up. The limit as x goes to 0 of -1 times the limit as x goes to 0 of 1 minus cosine x over x, right? That's that property. The limit of the product is the product of the limits. So what's this second one now? It looks familiar. It's 0. And what is the limit of any constant? Think about what the graph of -1 looks like. It looks like this, right? The horizontal line. What would be the limit anywhere on that line? The number itself, yeah. So the limit of a constant is just the constant. And of course, now what's -1 times 0? 0.
So I'm confused. Why doesn't it work if I was putting these, won't it still use 0 in the numerator?
It does, yeah, but it's not necessarily the same function. If you think of what the new function looks like, it's a -1 times the old function. So if the old function looked like this, let me kind of trace over it. What does multiplying any function by a -1 do to it graphically? It reflects it across the x-axis. So the graph actually looks a little bit different. But what I'm trying to show you is that the result at 0 still doesn't change. Yeah. Okay, so let's reevaluate. The sine of x over x as we approach 0 is 1. You can flip it and it's still equal to 1. And of course you could stretch it or compress it and even shift it as long as you approach a different value. The 1 minus cosine x over x equals 0. And although you can't flip it to get a number, you can flip it to get d and e. You can commute the subtraction. 1 minus cosine minus 1. It works to give you 0. So the easiest way to remember it is this, because some people do get them confused. The one that has sine of x in it equals 1, and the one that has cosine of x in it equals 0. So that kind of helps, right? Sine looks like there's a 1 in there for the I, and then cosine has a 0. But both of them only have that behavior at 0, as you're approaching 0. Okay, you got it memorized? Maybe I'll throw those on the quiz tomorrow just for 2 free checks. Okay, memorize them. So what are we going to do with them? We're going to use them. And that just summarizes what we've talked about. Yes? Oh, yeah, that's me. Yes, that's me on there. Very good. Let's look at this one. Example 14a. The limit as x goes to 0 now of sine of 7x over 6x. We're not really just going to ever have just plain sine x over x. Direct substitution gives us what? 0, 0. It doesn't work. It's got trig in it. We're approaching 0. It's got sine in it. Maybe we can manipulate it somehow to use what we've already memorized. Now, in order, what's that? The 7 would have to be in front? Correct, yes. Yeah, you can't pull the 7. The angles are sacred. Since you brought that up, you can't pull the 7 out. The angles are sacred in the sense that the only way to tamper with the angles is by using some kind of identity. Composite identity, half angle identity, double angle identity. So you do have more flexibility over the denominator, okay? Now, the only way that this is going to equal 1 is if these two numbers, in this case the 7 and the 6, are the same, right? Because then if they were both 7s, you would just be compressing it by a factor of 7. If they were both 6, you'd be compressing it by a factor of 6. So we either have to turn this 7 inside the angle into a 6, which I just said was going to be hard because you have to use identities, or somehow make the 6 into a 7. That's essentially what we're going to do. It's easier to multiply by a clever form of 1 than to use an identity. So you just wish the 6 in the bottom were actually a what? A 7. Because I'll summarize it right here. The limit as x goes to 0 of sine of mx over mx equals 1. Okay, and of course it works flipped as well. So your goal is to get these to be the same. And yes, you can multiply by a clever form of 1. So here's what we're going to do. We're going to say that it's sine of 7x all over x, and then over here off to the side, I'm just going to call that 1 over 6. Is everyone okay with that? That's the associative property of multiplication. In other words, that factor of 6 was of no use to me in the bottom because he wasn't a 7, so I'm just going to write him off to the side. Now I'm going to multiply by a clever form of 1. 7 over 7. Good. Now I'm going to associate it cleverly. So I'm going to put the 7 factor in the denominator in front of the x. And then the 7, I'm actually going to put it over there on top of the 6. So this is not just multiplying by a clever form of 1. This is cleverly multiplying by a clever form of 1 because I'm associating each 7 with a different factor. But of course, you could verify it's the same by going, and we're back where we started. So you don't want to do that. But now we're in business, right? Because we know from the property from 1.2 that the limit of a product is just the product of the limits. So what would be the limit of the first factor? It goes to 1 by memorization. And of course, what's the limit of 7, 6 as you approach any number? 7, 6. And now you get 7, 6. So really, are you trying to make a generalization already? Go ahead.
Sine of a different number. Sine of a x over bx. Just a over.
You're saying you see the 7, 6 in the problem already. So you're saying you want to make this claim already after just one piece of evidence that sine of ax over bx is equal to a over b. Is it safe to do that after one result? It is? Not really, but can we prove it? Sure, let's prove it. Let's do the exact same thing, but with variables. If you do it with variables, then it works. So we got the limit as x goes to 0 of sine of ax over x, and we'll call that one 1 over b. And now I'll multiply by a over a, so there's an a, and we'll turn that into an a, multiply by a clever form of 1. This, of course, becomes 1, and this becomes a over b. And it's that easy to prove. So yes, you're going to see a lot of different trends emerging. Is that one that's worth memorizing? Perhaps. Perhaps. Or if you didn't want to memorize it, you could just multiply by a clever form of 1 and arrive at it very easily. But if you want to memorize it, I'm not going to stop you. Okay, good. Letter B. Limit as x goes to 0 of 3x over sine of pi x. Direct sub gives you 0 over 0. So because it has sine in it, and it is, just broke my stylus tip. Got to have my finger now. That was a nice one. Yeah, it's okay. I got pi x there, and because pi is part of the angle, we're just going to kind of leave him alone. The 3 is expendable, so kind of the same idea. If I split this up into, let's see, the x is good. I got sine of pi x down there, and I'll put the 3 over here for now. And what would I love to have in the numerator as the coefficient of x? Pi. So I'll multiply by pi there as long as I divide by pi there. And now I'm ready to go. What happens to the first factor? 1 times the constant, and I get 3 over pi. So double K's little rule that you just saw, does it work when it's reciprocated as well? Yeah, it does. It does. So, yeah, you can come over here and say that, where do we yeah, this right here. It's also equal to the limit as x goes to 0 of ax over sine of bx, a over b. Okay? So if you want to memorize it, feel free. Manipulating trig expressions. All right, how about this one? Direct sub, never not first. You try this one. My throat's getting sore. You need to take about a 1-minute break. Try to evaluate it. I think you do get 0 over 0, just FYI. So that means...
Yeah. Oh, I thought we were just supposed to do 0 over 0.
Oh, yeah, now try to eradicate it. See, that means the limit exists because it's not Jumpman. What is the limit then? Function doesn't exist there, but the limit will. Are we getting the same results as last year?
Some of it's different.
Oh, I changed a little bit of it, yeah. Still 0?
Yeah.
Still 0, yeah. You do get 0 over 0. This one's kind of neat. You can factor out a 4 from the top. And you can factor a 4 out of the bottom. Like that. So really, 4 over 4 is 1. So this is really the same thing as this in disguise. And that one's ready to go. That's the other one we memorized. As long as the angle, and in this case the coefficient of x, are the same magnitude, it's going to be what we memorized because it's just going to compress it by a factor of 11. And this one, of course, was 0. All right, now they're going to get a little bit more interesting. Example 15. You get 0, 0. We can get that out of the way together. Can we do this? Sine of x over x goes to 1. Plug in a 0 to its left. You get 0 plus 1 is 1. No, that doesn't work. That'd be cool. Well, there's a hole at 0. We know 0 over 0 means there's a hole because it's not a jump man. We're approaching 0. That's good. We've got sine of x over x in there, so we're probably going to have to use the sine of x one. But how is that first term in the numerator going to be reconciled? Clever what? There you go. Separate. That's the deal. One of the strategies all year long, you can separate numerators easily. Put each term over the denominator. So write the limit first, get it out of the way. We'll come back at the end. X over x plus sine of x over x. And again, you could treat that now as two problems. What's the limit as x goes to 0 of sine of x over x? Or x over x? You get 0 over 0. So there's a hole in the graph of x over x at x equals 0. We already have the bad guy factor factored out, right? So divide it out. You're left with what? 1. So x over x is nothing more than the graph of the horizontal line y equals 1 with a hole at 0, 1. So that goes to 1. And what does sine of x over x go to? 1. And 1 plus 1 is 2. Yeah. Splitting it up.
So the x over x, you wouldn't plug in that 0, you just simplify it?
Well, if you do plug in this 0, you get 0 over 0, which is a hole, and then, of course, they divide out to give you 1. Yeah, and there's nothing to plug into. If they didn't divide out, then you wouldn't be getting 0 over 0 when you plugged in. Yeah, you'd get something else. And remember, 0 over 5 would be 0. 5 over 0 would be some type of infinity, which means D and E. So because it's 0 over 0, they do divide out. All right, try this guy. Zero over 0. No calculators anymore. We have to manipulate and use one of the two that we memorized, or both, possibly. I didn't know what to do, so I just started sketching some stuff. Just some random stuff. What? Split it up? What do you mean? Sine over cosine? Oh, not cosine over sine. Sine over cosine. Yeah. Yep, like that. Good. If the two that we memorized have sine and cosine in it, then when we're faced with tangent and 0 over 0, trying to express it in terms of sine and cosine is a great idea. So tangent is sine over cosine. And now you have a complex fraction, so in this case you can LCM over LCM or state change flip, which would end up being x cosine of x over sine of x. Now try direct substitution. Does that fix it? But now it's still the x causing the 0 on the top, but instead of the tangent causing the 0, it's the left sheet sine. We should be in good shape though, right? Because, and I'll just show the association here, x over sine of x, and then cosine of x. By memorization, what's the first factor? 1. And how do we evaluate cosine at 0? Plug in. It's continuous. So you get cosine of 0, which is 1. So your answer is 1. Wow. So it turns out that x over tangent of x worked out pretty much the same way x over sine of x worked out, yeah? And in fact, when we did our little analysis, x over sine of x actually emerged, and we were only left with the residual cosine of x, which at 0 is what? 1, the identity element of multiplication. What can we then generalize about that? Sine of x and tangent of x, same rule. They behave the same way around x equals 0, and that's why I drew this picture here. The pink graph is sine of x, the purple graph is tangent of x, and notice in the neighborhood of 0, they behave very, very, very similarly to each other. Sorry, I won't get it. So yes, you can replace those rules up here with sine. You can replace them with tangent. All these things right here with sine work exactly the same way with tangent, exactly. Okay, so you wouldn't even have to do that anymore. So let's try this then. Maybe we'll combine two rules in one. The limit as x goes to 0 of tangent of 4x over 3x. 4/3. Good. We generalized it. Double K is a little insight there. Sine of 4x over 3x is 4/3. It works the same with tangent. Tangents and sines, as you approach 0, interchangeable. Cool. How about this guy? Theta now instead of x. Direct sub. Let's go over that. Maybe. I think I can write them in terms of cosine. What is secant of 0? It's 1, because cosine of 0 is 1. This is the reciprocal of 1. So we do get 1 minus 1, which is 0, over 0 times 1, which is 0. And now because secant can be written in terms of cosine, that might be your first step there. So very carefully, 1 over cosine minus 1, all over theta over cosine in the bottom. State change flip could work here, but in this case, I think I'm going to do LCM over LCM. Cosine in the top, cosine in the bottom, and let's see what I end up with. Distributing, you get 1 minus cosine. And the bottom, your cosines divide out, leaving you theta. So yes, Megan, this is, in fact, what? 0. Yeah, it's the cosine one. So this is exactly the one that we memorized, but in disguise. Notice what we did there was a tiny little trig proof right in the middle of a limit problem. We showed that the original expression equals 1 minus cosine over theta. Now we got like 4 minutes left. These are just fun. They're all kind of similar, but you need a lot of practice with them. How about that guy? Direct sub gives us what? 0 over 0. What to do, what to do. Who's causing 0 in the top? The sine of 5x, and who's causing 0 in the bottom? X. Here's what you can get in the habit of doing then. Start isolating the bad guys. The bad guys are the guys causing 0 over 0. I like to put them in beefy brackets because it reminds me of like a fortress, some strong holding still. Beefy brown? Okay. Those are the strongest of brackets, the beefy brown brackets. So in the beefy brown brackets then, I'll put sine of 5x in the top and x in the bottom. Those are the 0 over 0 guys. They're the bad guys. And then outside, in purple brackets, no, let's do wimpy parentheses. Because we're going to put good guys in there. We want the good guys to be able to break out. Or roam. Very good. The other factors go out there. Now, the other factors are not causing the 0. They're causing a 4 and a 1. Now, here's what you're going to do. By multiplying by a clever form of 1, you're going to create exactly what you need. I wish, oh wish, that there was a what down here with the x and there was a 5. So I'm going to throw that 5 inside that gel cell as long as I put a 5 somewhere else in the numerator. I cleverly multiplied by a clever form of 1, yeah? Okay, good. Now we're ready to go. What becomes of the first beefy brown factor? 1, and then everything else, direct substitution. 20 over cosine of 0 is 1. That's why he was in the good guy bracket. And the answer is 20. Okay. We'll stop right there. We'll finish tomorrow pretty easily. So it looks like 1.4 will be due on Tuesday. No, school Monday. Yeah. We'll have a little quiz tomorrow, though, too. Real short, just a couple limits, radicals, Jumpman, maybe 1 or 2 of these trig ones. So be ready for it. Test is next Thursday, yeah.